Okay, I think we're ready to roll. Good afternoon, everyone. So glad to see so many of you. Welcome. Thanks for attending my talk. My name is Kristof Neys. I'm a solutions engineer at Neo4j. The topic of today is age of reasoning. My mission is to make you as excited as I am around knowledge graphs, and also to show you how agents can help you reason on that knowledge graph. Okay. We're going to basically cover 5 main topics, 5 stops on our journey. We're going to kick it off lightly, so to speak, with discussing a little bit what reasoning is all about, how we reason. Then to look at how we encode nature. Then we're going to have a look at graph technology specifically, and then we'll touch a little bit on agents, what agents can do for us, and then we're going to do a demo. I'm not going to gamble with the gods, so I'm not going to do a live demo. I've recorded it, but then I can talk you through it a little bit. So, and then if you have any questions, we have a stand next to the Databricks one, N80. So come and see us. My colleagues and I will be there. Any questions that you have, also if you want to have a live demo, etc., then we can do that, of course. Okay, so reasoning. So let's start with a fundamental question, because that's going to lead it to the rest of what we're going to talk about. So like a working definition, as it were, that we can have, or a definition that we can maintain, is that it's ultimately a logical process where we connect facts, do inferences based on premises. And the key thing is that, we try to recognize patterns and connect events, as it were, and then come to some decision and conclusion. And there's 2 major branches of reasoning, as it were. There's the deductive reasoning, where we go from the top to the bottom. If I give you an example, all mammals reproduce. Last check, Elon Musk is a mammal, and the logical conclusion is that indeed he reproduces, and that's been proven by empirical evidence, of course, that he's done that. 14, I believe, by the last count, but we're Thursday, so we never know. And then we have another one that basically goes from the bottom up, as it were. So the sun shines today, so tomorrow it's likely to be shining while it rises as well, right? So all a bit theoretical now, but it's going to come back. Don't worry, this is not a physics lecture or any of that, or philosophy for that matter. But also think a bit like how you personally think, how you plan your day, how you go through the process, etc. So how we personally, leaving the theory aside, if I want to, after this, hopefully you will go home, not after my talk, I mean after after today. So, and then you say, okay, if I want to go from A to B, what are my options, as it were? Do I cycle? Do I take the overground or whatever? Is there rain? Is there not? And all these kind of things. And then eventually you say, you know what, it's a beautiful day. I'm going to jump on a bike and I'm going to cycle the shortest way. And you get that, right? So in your mind already, what we all do is compute some form of algorithm. We go through steps and we compute an algorithm. And typically you can see where this is going to go, right? Is that algorithms and graphs are related in that respect, right? And then so, as a human, the way we think, it's all a little bit messy. So we do run an algorithmic process, but it's all a bit messy. And machines, they need a lot more structure, as it were, right? So because that's ultimately the purpose of what we're doing here today, we want to capture that in some form of machine language in a machine readable form. So for a machine to reason to work, a computer to reason to work, we need a formal process on a structure, right? On a structure. So that's basically the claim that we make here, that we need to capture the world to really help us to do that reasoning. So first of all, we need a data model, okay? And so what is that data model? Well, no surprise, and I actually forgot to mention that, Neo4j is a graph technology company, and I'm going to talk a lot about Neo4j, but Neo4j has everything that you see and that we talk about here today is open source. So come and see us afterwards at the booth, because we can explain to you how you can implement this on your data free of charge, okay? And so yes, how do we encode this nature? And what I always like to start off with is that how is nature, how do we perceive nature? And that's a quote by DeepMind, who have really doubled down on graphs. They're saying graphs are the main modality of data we receive from nature. I think it's a pretty beautiful quote, as it were, because if you think about it, atoms. Atoms are nothing without the bonds that connect them, right? So at the molecular level, we have some connections, etc. At the personal level, at the societal level, we obviously, Facebook and what have you, we are connected, we interact, etc. And then indeed, like we just saw, the way our brain works, it's a neural network. So everything in nature is a connected way, connected format. And then let's translate that into sort of like machine-readable language or structures, as it were. What can capture that specific connectivity between our data points? And that is this concept of a knowledge graph. Okay, so a knowledge graph it's a data structure that has been in play not that long ago, actually, as a term. If you go into the literature, maybe it's been described a while ago, but it's sort of like Google that sort of like popularized it. And in terms of like its working definition, there's a few academic definitions, but the one thing that you need to, basically the thing you need to keep in mind is like three major components that make up a knowledge graph. There's first of all, we have entities that are then represented as nodes. So in this case, and that we'll see in a demo later on, those are, for instance, the tube network, so like the metro station or the tube station, London Underground. So we have Paddington Station that's connected to another station. So those are the entities. We have the central line or whatever line in between those entities, but that can be anything, right? So already you can perhaps think about how that could be applied and can be applied rather to your own data, etc. Because most of the data is, of course, connected. That's what we just saw in sort of like nature format, as it were. And then the key aspect as well of a knowledge graph, which is sort of like underappreciated almost, is that we can add properties ad infinitum to both the nodes and the relationships. So this can be anything like, can be an integer, can be a string, etc. And if we now look at what are so like the knowledge graph 2.0 that you certainly want to deploy, is one where you can add vectors. And one of the things that GenAI has thrown off now, left, right, and center, is yes, it can compose a story for my 5-year-old, as it were, a bedtime story, but also encoding models are now ubiquitous. I can convert any piece of text into a vector representation, and I really want to use that and add that into my knowledge graph, and so that is possible. So the thing with the knowledge graph is not only is it the right capture, encoding of nature, but it's also very much machine readable. I can include a lot, and then the other cool thing about it is I can run this at scale. I can run this at an industrial level. I can capture this in the billions and billions of nodes and even up to trillions of relationships. There's really no limit to it all. What we can also do, and we can talk about that later on perhaps, is that we can ingest real-time data in that knowledge graph if you have the setup correctly, etc. So it's a very versatile structure. The knowledge graph captures that structure of nature, as it were, right? Okay, so now that we have sort of like defined that knowledge graph, we've defined what reasoning means, the logical next step is then, can we basically do some reasoning on graphs, right? So can we do some computations on graphs? And we've already seen it earlier, if you want to go from A to B, etc. And part of these conferences that we come here is also basically to network and to make friends. So I'm going to make it as interactive as possible. So I'm going to ask you guys to speak to your neighbor for the next few slides and to debate a little bit or converse a little bit. Even if you don't know each other, it's a great opportunity. So spend some time with your neighbor to think about and to discuss where and what this means. And I'll let you debate for 20 seconds or whatever, and then a brave soul can certainly raise their hands. Any brave soul that wants to risk it? Anyone? Anyone has an answer? There. Sorry. A maths problem? Yeah, you're very close. But where is this? Königsberg, is that what you said? 7 bridges? 7 bridges of Königsberg, exactly. So 7 bridges of Königsberg is basically, back in 1732, what you did on a Sunday afternoon, you went out with the family after a nice lunch and you tried to cross those bridges only once and come back at the starting point. And there was this mathematician, Euler, that basically proved that this was impossible, okay? And with that, graph theory was born. Because now it's a major branch or major part of mathematics. And with graph theory came graph algorithms, okay? So we now have a way of basically computing various things on this, so like on a graph. As I said, we've been doing this for nearly 300 years. And one of the things, for instance, that we can do is like measure what is important in that graph, and those are centrality metrics, for instance. Or we can find communities on that graph. We can find the shortest path, as we saw earlier, and also we can find similarities. This is only the tip of the iceberg. For people that follow a little bit what DeepMind is doing, and if you've seen what they've done with AlphaFold, if you look into that workflow, part of that workflow was a graph structure and indeed a graph neural network. So these things we've only scratched here. If you take it further to machine learning, graph neural networks are vastly outperforming your traditional machine learning methods, etc., because it can learn from that connectivity. So we're basically leveraging that. And that reasoning on graphs, we already do this a lot. You may not know this, but again, you're going to have to speak to your, or converse with your neighbor. Here's the next question for you guys. Which is the algorithm that you personally most likely use a lot on a daily basis? And I'm not talking about hashing and sending packages over the internet. No, just basically that you consciously call without knowing you're doing it. So 30 seconds, go. I bet that most of you guys do it on a daily basis. Okay, I'll give you a tip. Does anyone still use Google? Anyone no longer use Google for search? So if you use, this guy no longer uses only ChatGPT, I guess. So basically, I mean, I'm cutting corners here a little bit, but in a nutshell, Google search was driven by a centrality algorithm called PageRank, right? So PageRank is something that we still use on a daily basis, or still sort of like use on a daily basis. So what I'm trying to get at is that graph algorithms are used daily. They help us reasoning. And then if we now tie it back in to what we said about what reasoning is all about, drawing these logical conclusions, having these two major branches being deductive and inductive, well, lots of these graph algorithms are actually doing that, right? They're either doing deductive reasoning, doing some inductive reasoning. PageRank is an example of inductive, et cetera, et cetera. So we already are applying a lot of these graph algorithms, which is very much close to the way we think, the way we reason, right? So we are there already. And then so that then brings the question, so now in this age of agents, right, can we use an agent to facilitate, to help us with that reasoning, right? Because the alternative is go and get a degree in data science, so to speak, and become a data scientist, et cetera, and do it all yourself, right? So that's the alternative. But can we have an agent now to facilitate that reasoning on graphs? And then, of course, yes is the answer, otherwise I wouldn't be here. So let's spend a bit of time on agents. As a working definition, I think this is a pretty good one. So it's a system that acts independently. Of course, it's not HAL 9000. It is basically something that you program yourself to solve a specific task. And for those who have looked into agents a little bit, you can then obviously string them together, but it's a very specific action that you wanted to do. And why do you need that now to work with LLMs and in combination of LLMs? Is that LLMs, of course, yes, they can answer a lot, but they are limited to whatever data they've been trained on, right? So they're not going to be able to answer any questions on your specific data, right? That is basically company-specific or whatever, right? And then you're going to say like, aha, but I've got RAG, don't I? I can do even graph RAG. Absolutely, right? And so that's what we're going to use in the demo as well. We're going to use a proprietary database with our own information. In this case, it's the London Tube map, but you can do whatever. But the clue in the RAG is the R. It's retrieval. It's not reasoning, right? So it retrieves information. It doesn't reason on that information. And that's ultimately where we're going to see where we can do better at, right? So already an agent supercharges that LLM, can draw a lot of stuff, right? So it can interpret the question. It can then plan for whatever it needs to do these function calls. And then the cute thing about it is that the results it gets back, it passes it back on to the LLM, then to let it work its poetic magic, as it were, right, to compose a sentence. But they're not there's a little bit of problem with these agents is that yes, you can call a Python script. Yes, you can do all kinds of other things, but they can't really reason like a graph algorithm can potentially reason, right? So they can't answer these questions: who's the most influential person? Which is my client base that can do that is the most important yesterday, etc., etc. And that's where we now recently, about a month ago, released a new agent. And to the best of my and our knowledge, it's the first agent that can do reasoning on graphs. And the better, even better, is that it's all at your disposal. It's all open. It's an open source. It's a GitHub repository, and there's various ways of implementing it. And we're going to see in a minute how to do that. So if you come to the booth later on, I can show you where the paper is, where you can get the paper. But so there's a paper on archive with a lot of the details. I'll summarize them here before we go into the demo. Basically, the way it works is that you ask a question, and we'll see that in the demo, to the LLM client. It then automatically, of course, what an LLM is good at is at interpreting, at learning, at understanding the actual question. It understands that it's some form of like a graph question that it needs to answer. It then ultimately matches the correct algorithm that it needs to use to solve that specific question. How does it do that? Because in the agent, in the building of the agent, we gave a description for each algorithm, and it can match that up. And then basically runs it on your proprietary database, which is your knowledge graph that you have in Neo4j, your specific data with all of the security requirements, etc., and privacy requirements. And then the results get returned to the LLM, and what we'll see in the demo, it can do some cute things with those results as well. The LLM, that is, right? Under the hood, it's an MCP server. We currently have about almost 50 algorithms, and that will be expanded. And then, yeah, it runs directly onto the knowledge graph. Okay, right. So let's see this business in action. So as I said, it's an MCP server that you need to connect to your LLM client. What we're using is a Claude instance. So if you're familiar a little bit with Claude, you can use the desktop version, and you can then connect and configure the MCP server. And it connects to the database, the graph database, to retrieve the information. All of that is handled by the LLM, by the agent, by the MCP server. So let's have a look. As I said, I didn't want to gamble with the gods, so I recorded this, but come and see us later on. So you basically connected through your to your MCP server, in your config file of your Claude. You ensure you install the GDS agent, and then you give it the credentials of your database, and that is a local database in this case, just on your laptop. And then I can ask it some questions, right? So let's say I'm starting off with a very basic and easy question. How can I get from Paddington to Hammersmith around the corner, or vice versa? And then it realizes it, okay, few quickest ways. That means I need to find the shortest path, right? Okay, first thing it does, it goes and collects some information from my database. Those are the nodes, the relationships, all kinds of properties. It has, once it's collected that information, it says, okay, fine, now I need to run a shortest path. He runs the shortest path, it gets some results, sounds good, but let me see if I can find an even better route. And so there's about 8, 9 path finding algorithms. So it says, why don't I go for a Jens shortest path algorithm, which is another kind of algorithm. It collects all of that data, and then ultimately passes on to the LLM again, and the LLM works its poetic magic and comes up with a summary. So that's fantastic. So that's already, you can see how it basically interacts with that, right? So what happens under the hood? There's a couple of things here. So it, first of all, as you saw, it collects data from the initial properties, the nodes and the relationships from that database. Then it learns from the question that it needs to run a path-finding algorithm. It decides the shortest path, Jens algorithm, and again, why and how does it do that? Because we've described it under the hood or in the in the actual agent. It then projects the graph into memory. That's a pretty cool thing. You don't have to do that anymore, because you're not going to run an algorithm on the database. You're going to run the algorithm in memory. The agent takes care of that. So you don't need to be a data scientist anymore. You don't need to even know what Neo4j is. It does it for you. And then, yes, it returns the results to LLM to work the magic, right? So let's have a look at a little bit more, more advanced questions, so to speak. So pathfinding is relatively easy, but what about a little bit more analytical engine? And so like, can I travel throughout the network without leaving the station, right? And he said like, oh, okay, that's a little bit more tricky. That's more like a community finding algorithm. I need to know whether there are islands in my graph. What is an island? That's a component that is basically a set of nodes that are not connected to the other nodes. It's a little bit more tricky to figure that one out, and it figured it out, right? So it said like, okay, I'm going to run a community detection algorithm because, again, it matches the intent of the question with the description of the algorithm. And then it comes up with some formula like more general knowledge that it knows of. It's saying this is a typically well-designed urban transport network, yada, yada. Obviously, we haven't got that in the agent, right? It knows that from its general information that it's trained upon on the internet that this is a well-connected algorithm, right? So you're leveraging, you're combining both this reasoning that you do on the graph with general knowledge it's gained during its training, right? So that's a powerful tool. And then let's step it up a little bit more just to show you how far we can go with this. I mean, the sky is the limit, right? But what if King's Cross were to close down? Which stations will see a critical overload? This is pretty powerful, right? You can be a telco company and a router goes down. You can be basically a distribution network and some distribution center has a fire or something like that. This is pretty advanced, pretty heavy lifting, because what it needs to do now, it needs to run so like these centrality metrics on, not only on King's Cross, but also on the various stations around King's Cross. It runs between a centrality. Between a centrality is an algorithm that computes the number of shortest paths that run through a particular node. And if you look into it in the literature, it's also deemed as an information bridge, right? So if you have a node where the high between a centrality, if that falls out, typically the network gets disconnected. So it runs that. It then runs shortest paths around, not only around King's Cross, but also around the other stations with a high between a centrality. There's a lot of information that comes back. So what does Claude do? He says, that's a lot of information. Tell you what, I'm going to run a report, an artifact, right? So it does that on its own, right? So again, you're leveraging this power of the LLM, and then it writes an entire beautiful report for you. If you're running a business, you want to know what customer segmentation you want to do, etc. These kind of workloads typically take you a lot of work, a lot of people to resolve, and to construct, and this is now at your disposal. All you need to do is ultimately model your data as a knowledge graph, which you leverage the connections of your data, store it into Neo4j, install the GDS agent, and you're off to the races, right? You're good to go. So there's a lot you can do with this. As I said, I think this is the first agent that actually runs graph algorithms. The key point I wanted to make is that a graph algorithm is really how we reason, how we think. Hopefully I've sort of like managed to illustrate that. And this is now at your disposal. So this is what you can do. Right, so I'll wrap it up. Well, I believe that said, like, reasoning is really understanding those connections. The knowledge graph, as DeepMind has stated, is really how we capture the data structure that is inherent in nature, inherent in our social interactions, etc. And then running algorithms of that one is the best proxy to do that reasoning on that data structure that we've now translated into a machine readable form. Thank you very much for attending. My name is Kristof. Come and see us after at the booth if you have any questions. We're also running a graph day next week in London. Come and see us if you would like to attend. If you like the talk, feel free to give us a review on the social medias, the LinkedIn. And with that, I'm at your disposal at the stand. Thank you so much.